This is going to start Chapter 7, which is on eigenvalues. And eigenvectors. And beginning with 7.1, which is our introduction, the eigenvalue / eigenvector problem. So we need our definition. We did define this earlier in the class, but I would like to define it again since this is now our main focus. So let A be an n by n matrix. Okay, so in other words, a square matrix. Any value of lambda for which A times V is equal to lambda times V has a non-trivial, just to remind you what non-trivial means, this really means non-zero solution solutions V are called eigenvalues of A. Eigenvalues of A. The corresponding non-zero vectors are called eigenvectors of A. Okay, so let's look at this equation more carefully. This is the vector equation that we're going to be looking at. Okay, this is saying that if you multiply a vector by a matrix A, you end up just with some scalar times the vector. Okay, and of course this is true if V is 0 for every lambda or any A, and this is why we exclude the 0 vector. Okay, so we care about where this happens where it's not the 0 vector. So let me just write a couple of notes here. So note 1, geometrically, this means the vector just gets stretched by the transformation. Okay, so if we were to look at this in terms of a transformation, right, T of V is equal to A times V, which is just equal to lambda times V. If this happens, this means that all the transformation does is stretch that particular vector. Okay, so this is the first note. Second note. If V is an eigenvector of A, then so is any scalar multiple of V. So what is the proof? Well, let's suppose that A times V is equal to lambda times V. What would A times CV equal? Well, we know that this is equal to C times AV, which is C times lambda V, which is lambda times CV. So what did we just show? We just showed that if you multiply any scalar multiple of the vector by A, you end up with lambda times that same vector. Okay? So in other words, any eigenvector of A corresponds actually to an infinite number of eigenvectors. Okay? So we only care about one of them. So let's write this down. If V is an eigenvector with eigenvalue lambda, then V corresponds to a set of eigenvectors. Right? Since any multiple of V is also an eigenvector, we have a complete set of eigenvectors of lambda. And what would that be? It would be the span of V. But we're taking away the zero vector. In other words, we're okay with anything times V except for the zero vector. Okay? This is the set of all eigenvectors of lambda. Okay, so as soon as you find an eigenvector of lambda, you have to take its entire span, but of course you don't allow 0 times that vector, but all of the other multiples of that vector are eigenvectors of lambda. This would be the set of all eigenvectors, or sorry, I shouldn't say of lambda. Let me write this a little bit better. Of all eigenvectors with eigenvalue lambda. Okay. So let's do an example of how to actually find these eigenvectors, or not how to find, but let me actually do an example where we demonstrate or show that something is an eigenvector with a particular eigenvalue. So we start with a matrix, so example. Let's let A be the following matrix: -2, 6, 5, -1. We want to show that V1 equals -1, 1, and V2, which is equal to 5, 6, show that these two guys are eigenvectors of A with corresponding eigenvalues lambda 1, which is -7, and lambda 2, which is 4. Okay? So we want to show that this guy is an eigenvalue or eigenvector with this eigenvalue, and we want to show that this guy is an eigenvector with this eigenvalue. Okay, so these are corresponding, they go together. So how do we show this? Well, we just multiply the matrix times the vector. So what is A? Let's write this down carefully here. So what is A times V1 equal to? That would be -2, 6, 5, -1 times vector -1, 1. So if we multiply these together, on top, what do we get? We get 2 plus 5, which is 7. On bottom, we get -6 minus 1, which is -7. And we notice that this is -7 times the vector that we plugged in, isn't it? Right? So we multiplied it by, let's use the same colors I used above. We multiplied this vector and we got this scalar times that vector. So that shows that this guy is an eigenvector and -7 is its eigenvalue. Okay, let's do the second one. What happens when you multiply A times V2? We have -2, 6, 5, -1, and then 5, 6. What do we end up with? So we have -10 plus 30, that's 20. And then 30 minus 6 is 24. We notice that this is 4 times the vector that we plugged in, right? So this is equal to 4 times 5, 6. Okay. All right, so we have just showed that when you put in this vector, you get this scalar times that vector. So this means that we're done. Okay. Something interesting that I want us to note, okay? What happens if we add these two vectors together? So I want us to let V3 be V1 plus V2. Let's add our two eigenvectors together. We get 4, 7. And let's go ahead and check to see what A times V3 is. We get -2, 6, 5, -1 times 4, 7. What is this equal to? We end up with -8 plus 35 is 27, and 24 minus 7 is 17. And you notice that this is not equal to a scalar multiple times what we started with. Okay? So why did I show you guys this? This wasn't part of the problem. What did we conclude from this demonstration? We just concluded that the sum of two eigenvectors is not necessarily an eigenvector. So let's write this down. This is extremely important. So this means the sum of two eigenvectors is not necessarily an eigenvector. Okay, super important. In other words, finding eigenvectors is kind of a unique thing, and you cannot get more just by adding them together. So this last example demonstrated how you would show that something is an eigenvector, but where did those vectors come from? In other words, how would we have found those ourselves? So we're going to learn how to find eigenvectors. So given a matrix A, how do we find eigenvectors and their eigenvalues? So here is the trick. We know that this is the equation that we care about, right? AV is equal to lambda times V. Okay. What does this mean? Okay, this actually means the same. So this means the same as AV minus lambda V equals the zero vector. Okay. What does this mean? So this actually means the same thing as the following. This means that if you take out a V on the right, you actually get this, A minus lambda I times V is equal to 0. What is I? Let me remind you guys that I is equal to the identity matrix. Okay? What kind of an equation is this? So I want to remind you guys that what we are looking at here is actually an n by n homogeneous system. N by n homogeneous system. So when does an n by n homogeneous system have a solution that is going to be an eigenvector? Well, remember, any non-trivial solution, let me write this down. Recall, since eigenvectors are non-zero, any non-trivial solution to the system will be an eigenvector. So what's the danger here? Well, can a system like this have no solution? No, because the trivial solution always works. And so what we care about then are the non-trivial solutions. In other words, that can only happen if we have infinitely many solutions. And so we can actually use the determinant to help us out. Okay? Since eigenvectors are non-zero, any non-trivial solution, so the system has a non-trivial solution if and only if the determinant of A minus lambda I is equal to 0. Right? As soon as you have a determinant of 0, we know that the system has no unique solution. It has to have infinitely many, and those are the ones that we care about. This is the most important thing you have to remember from this section. This is the key to finding eigenvectors, is this equation I just boxed. Okay? So let's go ahead and write down some steps. So these are going to be the steps for finding the eigenvalues along with their corresponding eigenvectors of a matrix A. So step 1, find all scalars lambda such that the determinant of A minus lambda I is equal to 0. Okay, so you're going to find these. There could be more than one. There could be one, but there could be 2, 3. It could be any number of them. We're going to talk about how many it can have a little bit later. But for now, just understand that this is how you find them. So these are the eigenvalues. So finding the eigenvalues comes first. Step 2. For each eigenvalue from, so let's suppose that you have k of them, lambda 1 all the way to lambda k. So for each one, find the solution set. Let me write it this way though. Find the non-trivial solution set. For the system. Let me write homogeneous system. Okay, so for each eigenvalue, you solve this homogeneous system, and each lambda I gives you a set of eigenvectors. You could write it this way. C times VI such that C is not 0, or this is the same as the span of VI, take away the 0 vector. Okay? So this is the process, okay? I mean, I'm writing 2 steps here, but this is a pretty involved process, okay? Because we're saying find all scalars. There could be many of them. Find all scalars lambda such that that is true. And then for each one, you're going to solve a homogeneous system. Okay, so you potentially have to solve a lot of different systems of equations. We have names for these things. So let me name these different equations that we are talking about. So let's first go with a definition. Given an n by n matrix A, the characteristic polynomial characteristic polynomial of A, which we denote P of lambda, is as follows. The determinant of A minus lambda I. Okay, so this is called the characteristic polynomial, and the characteristic equation is when you set that equal to 0. P of lambda equals 0, which is the same as the determinant of A minus lambda I is equal to 0. Now you'll notice that this is a 0 constant, not a 0 vector. I failed to say that before. This is an important distinction, right? The determinant of A minus lambda I, remember, is a real number, but with lambda in there, it actually becomes a polynomial. And so what you're doing is you're setting this polynomial equal to 0, and that is exactly when you're going to have infinitely many solutions to the system. Okay? So let's write down some facts about P of lambda, this characteristic polynomial. Okay? So note, if A is an n by n matrix, we know that when we take the derivative of, the determinant of an n by n matrix, we normally have to multiply lots of stuff together, but what happens is if you're going to have a lambda times I in there, you're actually going to end up with an nth degree polynomial. P of lambda has degree n. What does this mean? This means that P of lambda equals 0. In other words, the characteristic equation, because it's an nth degree equation, has at most n eigenvalues. At most n eigenvalues. An important characteristic, you might not have any, right? But it has at most n eigenvalues. Why at most? We know that there are n solutions to this thing, however, a lot of them might be repeated. So you might get a repeated root n times. We know that that's possible. So you could have as little as one eigenvalue. You're going to at least have one, but you might have up to n of them. Okay, let's go ahead and write down a theorem that is important. What could we say about an n by n matrix being invertible? An n by n matrix A is invertible if and only if 0 is not an eigenvalue of A. Well, I said this was important, actually. Thinking about it a little bit more, it's actually not that useful. It just, when you have an invertible matrix, you know that 0 is not an eigenvalue. Let me say why really quick. So why? Well, what would A minus 0 times I be? Okay. A minus 0 times I is just A minus the 0 matrix, which is just A. So the determinant of A is clearly not 0 since A is invertible. So this just shows that if A is invertible, then the determinant of A is not 0, which means that the determinant of this guy is not 0. In other words, 0 is not an eigenvalue. Okay, so that's really the reasoning right there. So in practice, solving P of lambda equals 0 can be really difficult if n is more than 3. Why? Because if you're trying to factor anything that has higher degree than 3, so since factoring a 4th degree polynomial is usually quite difficult. We're going to see that factoring even a 3rd degree is quite hard, can be quite hard. So for the next example that I do, or I'm about to do an example where I find an eigenvalue of a 3 by 3 matrix, and you're going to see that it's a little challenging to do this factoring. We have to be really careful with our algebra. Okay, you're never going to be asked to do a problem with n bigger than 3 just because it's just too hard for a human to factor it themselves, right? You would need a computer to do it. Okay, but 2 by 2s or 3 by 3s are what we're namely going to be dealing with. Okay, so we're going to do an example. Let's write this down on the next page. We're going to find all eigenvalues and eigenvectors of A, which is going to be 5, -3, -3, 12, -10, -12, and -6, 6, 8. Okay, because this is our very first, this is the first time that we are finding eigenvalues, I want to make sure that we all understand what the characteristic equation and characteristic polynomial actually looks like. Okay, so we're going to start by finding the characteristic polynomial. So what would P of lambda be? Remember, it's the determinant of A minus lambda times I. Now, just to be clear, we're using the 3 by 3 identity matrix here. 3 by 3 identity matrix here. So what is lambda times a 3 by 3 identity matrix? So this is going to be the determinant of, we've got matrix A, minus, if you multiply lambda times an identity matrix, you get the following: lambda, 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 0, 0, 0, 0, 0, 0, right? So you subtract these. What do we end up with? We end up with the determinant of, we have 5 minus lambda, -3, -3, 12, -10 minus lambda, -12, and -6, 6, 8. So this is the determinant that we're taking. Okay. This is going to be a very common thing that we do all the time, so we just need to get used to this. And what I'm going to do is I'm going to expand, okay? I'm going to expand on the top row. Now, we're going to be really careful here because this is going to involve a lot of heavy algebra. Let me write it this way. This is going to equal 5 minus lambda times, remember, we are looking at this matrix here. It's going to be, let me write it in a different color. We're going to do the determinant of this smaller 2 by 2 matrix, right? So it's going to be times negative 10 minus lambda times 8 plus 6 times 12, so plus 72. Okay. Then what? Then we go to the next guy, 12. So then what's left is the determinant of this 4 by 4. So it's going to be, minus 12 times sorry guys, I just realized that I forgot to write in the right. Let me go back. There is a mistake here. Let me fix this. Because when I do 8 minus lambda, I actually should be getting an 8 minus lambda on the bottom corner here. So let me erase this. This actually should be 8 minus lambda here. That would have screwed everything up right now, but luckily I caught it before it made a difference. Did I? No, I guess actually my first multiplication was wrong. Let me fix that here. Let me fix it here. There we go. Told you guys that algebra is tricky. So now I'm doing the minus 12, and I have, what do I get when I multiply these out? I get negative 3 times 8 minus lambda. That's equal to 3 lambda minus 24. No, is that right? Minus 12. Yeah, it's 3, that's correct so far. And then it's 3 lambda minus 24, but then plus 18. Okay, and then finally minus 6 times, we get, let me see, I'm doing, multiply those together. I get 6 minus 3 lambda, because I'm going to multiply, right? We're doing 36 minus, and then negative 3 times negative 10 minus lambda. So if you actually multiply this out, you end up with 3 negatives times the lambda. So you actually end up with negative lambda, and then the rest of it is the 3. So it's 6 minus 3 lambda, okay? 6 minus 3 lambda. What does this guy simplify to, by the way? This actually becomes 3 lambda minus 6, okay? What about this? If you actually work the algebra out and you multiply that out, I have worked it out in advance, believe it or not, you actually get the following. This is lambda plus 4 times lambda minus 2. Now here's the algebra trick. Before you go ahead and you multiply this whole thing out, you're going to get a giant cubic equation, which is just too difficult to factor. So the trick is to see if you can factor things out while you work on the problem. Okay, so here's the key. Can't I pull a 3 out of this right here? If I pull a 3 out of that, then I end up with the following. Negative 36 times lambda minus 2. And I notice I have a lambda minus 2 in the first, a lambda minus 2 in the second. Notice here that if I pull out a negative 3, I get the following. Plus 18 times lambda minus 2. And the trick here then, let me underline what I'm doing here. All three of these have a lambda minus 2, which means that I can factor out the lambda minus 2 by grouping. Okay, so if I pull out lambda minus 2, here's what I'm going to end up with. You pull out the lambda minus 2, and what's left? You're going to be left with 5 minus lambda times lambda plus 4. What do we get? Let me write it this way so that you guys understand the algebra. 5 minus lambda times lambda plus 4. Over here we have a minus 36, and then we have a plus 18, right? Because I pulled out the lambda minus 2 from all three of these terms, and this is what's left. So what I'm left with, if you simplify all of that stuff inside, simplify all of this, you actually end up with the following. I'm going to go to the next page here. This is equal to lambda minus 2 times negative lambda squared plus lambda plus 2. And if we pull out a minus 1, we end up with lambda minus 2 times lambda squared minus lambda minus 2. Okay. Which is, I can factor this, right? The whole reason that we did all this factoring by grouping is that we know how to factor quadratics from algebra. So this is equal to negative 1 times lambda minus 2 times another lambda minus 2 times lambda plus 1. Right? Because this thing I underlined over here factors into lambda minus 2 times lambda plus 1. So what did we just show? We just showed with all that work that P of lambda is equal to negative 1 times lambda minus 2. Let me write it this way, lambda minus 2 squared times lambda plus 1. And so what is the characteristic equation? Because what I have here is the characteristic polynomial. It's just a polynomial. The characteristic equation is if you take that thing and you set it equal to 0. And that's what we want to do so that we can figure out what lambda is. So this is why we factored it, right? This means that we actually have two solutions. We're going to call them lambda 1. Lambda 1 is 2. And lambda 2 is equal to negative 1. So these right here are two eigenvalues. Yes, that is a lot of work, a lot of algebra, but this is the process. Okay, so now we find the set of eigenvectors for each lambda I. So let's start with lambda 1 is equal to 2. This means that we have to solve the following system. So solve in this case it's a 3 by 3 homogeneous system. The system that we are solving is a minus 2i times v is equal to 0. How do we solve that? We practice doing this quite a lot in chapter 2, right? We practice solving systems of equations. So what we want to do is we want to look at the augmented system, right? In other words, we want to look at a minus 2i and then adjoin the 0 vector to that. Let's just go ahead and call that a minus 2i sharp, because that's what we're really looking at. So what are we going to do? We're going to take a and we're going to subtract 2 times the identity. Okay, so just take away 2 from every element of a that's on the diagonal. So it looks like this: 3, negative 12, right? And I'm doing the diagonals first. I took away 2 from every diagonal, and then I'm going to write down the rest without changing it. So 12, negative 6, negative 3, 6, negative 3, negative 12, and then 0, 0, 0. Okay, so this is what we get. How do we solve the following? Because remember, we're interested in the solution set here. So we're going to multiply row 1 by 1/3. And we're also going to just add the first row to both of the other rows because we notice that they'll immediately go away. So I'm going to add 1 times row 1 to row 2. And I'm also going to add 1 times row 1 to row 3. So if we do that, we get the following. Multiply that by 1/3, 1, 4, negative 2, and then everything else is a 0, right? So this is what we're looking at. So let's go ahead and solve here. We have 2 free variables, don't we? We have a free variable for this column and this column, right? This is, remember, these are the x2s and these are the x3s. So let's go ahead and start our free variables. We're going to let x3 be t and x2 be s. And then x1 is going to be negative, or 2t minus 4s. Let me just write it that way, 2t minus 4s. Okay. Or negative 4s plus 2t, same thing. And so what are the set of eigenvectors going to be? We can write it this way. We're going to write negative 4s plus 2t st, such that s and t are not both 0. We need to throw out the 0 vector, right? Because if you make everything 0, you get the 0 vector. We do not want that. Okay. Now, how would you actually write this as, I mean, this looks kind of weird right now, right? But if you notice something here, doesn't this equal s times negative 4, 1, 0, plus t times 2, 0, 1? So another way that we can write this, and this is the better way, we write this as the span of these two vectors. But we take away the 0 vector. So this is called the set of eigenvectors for corresponding to eigenvalue of 2. Okay, here they are. These are all eigenvalues, which we know that this is actually a plane through the origin, except we remove the origin itself. So it's like a punctured plane. It means any vector on that plane, as long as it's not the origin, gets stretched and by a factor of 2, right? Because the eigenvalue is 2. Okay? That's just for one eigenvalue. Now we've got to do the other eigenvalue. So let's do this on the next page. Lambda 2 is equal to -1, right? So now we need to solve the following system. Remember, it's a minus lambda I. In this case, this is going to be a plus I times v is equal to 0. So we are going to deal with a plus the identity augmented. What is this equal to? Well, now we're going to add 1 to all of the diagonals of the original matrix that we had. So I'm just going to add 1 to all of them. I have a 6, I have a -9, and I have a 9, and then I have 12, -6, 0, 0, 0, 6, -3, -3, -12. How do I solve this guy? Well, I've already done the work in advance, so if we go ahead and we do all of our row reductions and all that, we end up with the following, okay? So I'll just say with row operations, we end up with the following: 1, 0, 0, 0, 1, 0, 1, -1, 0, and then 0, 0, 0. How many free variables do we need this time? Well, only 1, right? Because this is the only column that does not contain a leading 1. That's for x3. And so if we make x3 equal to t, x2 would also be t, and x1 is -t. And so what we end up with is the set -t, t, t, which is the same as t times -1, 1, 1. So we can write the set of eigenvectors now. This is equal to the span of -1, 1, 1, take away 0. Okay. So this is the set of eigenvectors for eigenvalue -1. Okay, so these are our two solutions, right? We had this eigenvalue with this eigenvector, and then we had, for this eigenvalue, we had that set of eigenvectors. So this last example demonstrated the process for finding all of the eigenvalues and eigenvectors. Suppose we were asked instead to write all the linearly independent eigenvectors corresponding to each eigenvalue. So how would we write that? Well, for lambda 1 equals 2, how many linearly independent eigenvectors did we have? Well, look at it. we had two, didn't we? We had this one and we had this one. Okay, so let's write that down. Let's call them V1 and V2. We had V1 equal to -4, 1, 0, and V2 was equal to 2, 0, 1. For lambda 2, which is -1, we had only one eigenvector, didn't we? -1, 1, 1. Do you guys see it? It's right here. Linearly independent, I mean, obviously, right? Because it spans a whole set, but I'll call it V3. This is equal to -1, 1, 1. Okay? Notice that we have, so notice that A, which was a 3 by 3 matrix, had or has 3 linearly independent eigenvectors. We actually have a name for this, okay? Therefore, A is called non-defective. Non-defective. Actually, I think the book might actually abbreviate this with, or not abbreviate this, sorry, but put a little dash mark there, so I'll copy what they do. Non-defective. Now, A was a 3 by 3 matrix. It had 3 linearly independent eigenvectors. The question is, does this always happen? Well, you can guess that because I called A non-defective, there would be such thing as a defective matrix, right? Maybe a matrix that does not have all n eigenvectors. So let's ask this question on the next page, okay? So question: does every n by n matrix A have n linearly independent eigenvectors? So as you can guess, the answer is no. All right. So let's do another example. We're going to find all eigenvalues and eigenvectors of A, which is going to be the 2 by 2 matrix 1, 1, 0, 1. Okay. So let's remember the process. We start by writing P of lambda. P of lambda is the characteristic polynomial, and this is going to equal the determinant of A minus lambda I. So you just take away lambda from the corner or the diagonals, right? So we get 1 minus lambda, 0, 1, 1 minus lambda. Oops, sorry, it's the determinant of this. We can also write it this way. I'm going to write it with bars. How about that? We know it's the determinant of this 2 by 2 matrix. So lucky for us, this is actually just 1 minus lambda squared minus 0. But that's just 1 minus lambda squared. Good news, it's already factored. Quite nice, quite easy. So if we set that guy equal to 0, 1 minus lambda squared is equal to 0. This implies that lambda equals 1, and so we only have one eigenvalue. Notice that it has multiplicity 2. I'm going to write that down. Multiplicity 2. All of this stuff we're going to explore in greater detail in this chapter. okay? But we're writing all of this down now, keep a record, okay? So we want to find the eigenvectors, okay? So for the eigenvectors, remember we only have one, so for lambda equal 1, we want to solve the system a minus 1 times I, or just I, v is equal to 0. Okay? So what is a minus I augmented equal to? Okay, take the original matrix A and subtract away 1 from the diagonals, and we end up with 0, 0, 1, 0, 0, 0. How many free variables do we have? We just have one free variable, which is x1. So this means that x1 is t and x2 is 0. So what do we end up with then? We get t0, which is the same as t times 1, 0. And so what would the set of eigenvectors be? It would be the span of 1, 0, take away 0. How many linearly independent eigenvectors? So let's do this on the next page. Notice A is a 2 by 2 matrix with only one linearly independent eigenvector. This implies that A is defective. So now we've seen this word and we understand what it means. We will define it formally later, okay? But the point is that if you we're going to learn that this is called having a complete set of eigenvectors. If you have a complete set of linearly independent eigenvectors, meaning you have n of them, A is going to be called non-defective. And if you do not have enough eigenvectors, then A is called defective. All right, that was a nice long example. We're going to do a little bit more in this, not too much more, one more example, but I want to talk about complex numbers also, okay? So note, even though we've been getting real numbers, we know that when you solve equations, sometimes you have complex solutions. So note, eigenvalues can be complex numbers also. Okay. What does that mean? So eigenvalues can be complex numbers also, and not just eigenvalues, but also eigenvectors as well. What do we mean by that? Well, this means that you might get an a plus bi. Remember, complex numbers, I is the square root of -1. A plus bi. And what about an eigenvector? What do I mean by a vector being, well, let's say we were talking about R2. Or not R2 in this case, right? We're talking about C2. What would C2 be? It means that you have vectors that are two sets of complex numbers. So it would look like this: C plus DI and then E plus FI. Okay, so it is possible that you're going to get complex numbers all over the place. Everything that we've said above still holds. However, for complex numbers, we have a time saver. Okay, first, let me remind you guys of an idea from complex numbers, or I guess you could say you learned this in intermediate algebra, an idea of a complex conjugate. Okay? What is a complex conjugate? So recall, if z is equal to a plus bi is a complex number, z bar, which is just going to be a minus bi, is called the complex conjugate of z. So anytime that you have a complex number, you also have another complex number called its complex conjugate, and that's designated with a bar on top. Okay, hopefully you've seen this notation before, but if not, it's pretty simple. So there it is. Okay, so when dealing with eigenvalue problems, involving complex numbers, the following theorem can save us lots of time. So let's write down this theorem. If A, or let me just not say if, let me say let A be an n by n matrix, suppose A has a complex eigenvalue, lambda 1, which we're going to call A plus bi, or let me not put coordinates here. Suppose A has a complex eigenvalue lambda 1 with corresponding linearly independent eigenvectors, or eigenvector v1, then A also has another eigenvalue, lambda 2, which is going to be lambda 1 bar. And not only do we know automatically another eigenvalue, this guy has corresponding eigenvector. Let's call it V2, which is actually going to be the first V1 bar. Super useful theorem, okay? It means that all the work you do to find one complex eigenvalue eigenvector pair, we can do that work. We could save having to do it again. We automatically have another pair that goes with it. Okay? Another thing I want to remind you guys before I do the next example is sometimes, this is a fact from algebra, recall that sometimes a second degree polynomial ax squared plus bx plus c equals 0 does not factor. In this case, you can still solve it. by using the quadratic formula. Remember the quadratic formula? Plus or minus the square root of b squared minus 4ac all over 2a. I'm writing it down. I'm assuming most of you guys remember this, but if not, there it is. Okay, we are going to use a lot of this stuff in the following problem. Okay, so let's do the example I wanted to show you guys here. Find all eigenvalues and eigenvectors of matrix A, which is 9, -1, 37, -3. Okay, so you're not going to know that you have complex answers until you actually work the problem out, because you don't know what the polynomial is going to look like until you actually solve it. So let's go ahead and write down p of lambda, which is our characteristic polynomial. Remember, this is the determinant of, you take away lambda from each of the diagonals. So it's 9 minus lambda, -3 minus lambda, this is 37, this is -1. We do this determinant. So what do you get when you multiply this out? You get the following polynomial. You get -27, let's see, plus 3 lambda minus 9 lambda, that's minus 6 lambda, and then plus lambda squared, and then minus a negative is plus, so plus 37, which is the same as lambda squared minus 6 lambda plus 10. Now notice we want to set this equal to 0 and we want to solve it. However, if we try as hard as we want, this guy does not factor. Okay, so we can go ahead and use the quadratic formula. So the quadratic formula says that lambda is going to equal -b, that's 6, plus or minus the square root of b squared is 36, minus 4ac, so minus 40, all over 2a, so 2. What is this equal to? This is equal to 6 plus or minus the square root of -4, all over 2, which is equal to 6 plus or minus 2i, all over 2. And this is where you have to remember how to deal with complex numbers. This is actually the complex number, or set of complex numbers, 3 plus or minus I. Okay, 3 plus or minus I. So let's start with, and we notice right away, by the way, that if we call lambda 1 equal to 3 plus I, and lambda 2 is 3 minus I, we do have two eigenvalues. They are complex. And notice, of course, that the first part of the theorem is true, that lambda 2 is just lambda 1 bar, right? Because 3 minus I is the complex conjugate of 3 plus I, and vice versa. So let's go ahead and figure out the eigenvalue. And here you're going to see why the theorem is so nice, because dealing with complex numbers can be a bit of a pain. So let's go ahead and jump to solving or finding the eigenvector. So for lambda 1 equals 3 plus I, we want to find the eigenvectors, right? And so to do that, we want to solve the following. A minus 3 plus I v equals 0. I know this looks weird because we have a 3 plus I in there, but you have to just treat it like a number, okay? It's not going to change how you do the problem. So we want to look at A minus 3 plus I augmented. This means you take away 3 plus I from the diagonals of the matrix. Okay? So, what does that look like? Let me write this all out because it's probably been a while since you guys have seen complex numbers. I'm going to write it like that, like that, like that, and then it was a -3, so I'm going to subtract this. This is what we're looking at. Okay? What does this become? When we actually do the subtraction, we end up with 6 minus I, 37, -1, -3 minus 3 plus, let me actually subtract that. -3 minus 3 is -6 minus I. What now? I'm going to permute the first and second row because I already have an almost 1 in the second row, right? So I'm going to permute rows 1 and 2, and we're left with -1, -6 minus I, 0. And then 6 minus I, 37, 0. And I'm going to multiply row 1 by -1. Multiply row 1 by -1. We get 1, 6 plus I, 0. And then 6 minus I, 37, and then 0. Okay. Now what? Well, you can eliminate this guy by taking -6 minus I, add it to row 1. Multiply by row 1 and add it to row 2. What do we end up with? So here's the thing, guys. I want to show you a cool trick. Yes, this is 0. Yes, this is 0. What is this guy going to be? Well, instead of actually multiplying -6 minus I times 6 plus I and then adding it to 37, okay, I'm going to show you that this is just going to be a 0, and we can make that assumption right off the bat. How do we know that it has to be a 0? Because you are guaranteed to get a row of zeros, at least one row of zeros at the very bottom when you do any eigenvalue problem, right? Because you always are going to have a free variable. I want you to look back. Every single eigenvalue problem we've done, let's go back to this example. When we solved it, we got a row of zeros, right? Or let's look back even more. We had a row of zeros. We're always going to get a row of zeros at the bottom. Was that all the examples we've done? I think so, right? We've only done those. The point is, we always have a row of zeros. You can't just make them zeros, but we have this trick for a 2 by 2 matrix. So I'm going to write this trick down. So let me just write this down. Trick for 2 by 2 matrices only. When solving A minus lambda I, or let me not say when solving, when putting A minus lambda I augmented into row echelon, we can immediately make the bottom row all zeros to save time. Okay, I'm writing this trick down, but please use it wisely. And what I mean by that is I cannot stress enough how important it is that this is for 2 by 2 matrices only. The reason why is because you know that ultimately in 3 by 3s or 4 by 4s, you are going to end up with zeros on the bottom, but that's going to require the rows above it to change, right? So you don't know what the end result of those rows is going to be. So you actually have to do those operations. But when you have 2 by 2s, there's not the first row is not going to change, okay? Because a multiple of that row has to give you the second row. In other words, the rows have to be proportional to each other. Okay, so let's continue on. Let's continue on from this, right? This is where we are. We're right here. We're going to go on to the next page. So actually, let me rewrite that matrix because I want to make sure we're looking at it while we talk about this. We have 1, 0, and we had, what did we have? 6 plus I, that's right. 1, 0, 6 plus I, 0, and then 0, 0, right? And so we have a free variable right there. So x2 is equal to t. What is x1 equal to? It's equal to negative 6 plus I t, okay? Or this is the same as negative 6 minus I t. So what do the set of eigenvectors look like for this set? It looks like this. Right? Because if we pull out a t, that's what we get, okay? In other words, we have one linearly independent eigenvector for lambda 1 equals 3 plus I, and it is negative 6 minus I 1. What would the complete set be, by the way? We have span of negative 6 minus I 1, take away 0. Okay, this is our set for that eigenvalue, and this is our linearly independent eigenvector. Let me, you know what, I was a little messy here. Let me call this V1. Okay, this is our linearly independent eigenvector. Now, remember, if it wasn't for the theorem, we would have to do this again for the other eigenvalue. So what about for lambda 2 is equal to 3 minus I? By the theorem, we know what the other eigenvector is going to be. It's going to be the complex conjugate. This will also have just one linearly independent eigenvector. And what's it going to be? V2. We're going to call that V2, and that's just going to be V1 bar. You take the complex conjugate of V1, so negative 6 minus I becomes negative 6 plus I. You just flip the sign of the imaginary part, and because 1 is a real number, there is no imaginary part. It's just going to be a 1. Okay? So that's it. One linearly independent eigenvector. And isn't that cool? We did not have to do the whole problem again. Nice time saver. So we illustrated two time savers here, this complex number theorem and then the trick for 2 by 2s that you can just make the bottom guys all zeros. Okay. Another way to write the answer for the problem we just did is for lambda 1 equals 3 plus I, the set of eigenvectors is what was it again? I think it was negative 6 negative 6 negative 6 plus I 1 take away 0, and for our second eigenvalue 3 minus I set of eigenvectors is span of that guy, take away 0. This is just another way of writing our answer. Okay. And just to make sure we understand our terminology, remember A was a 2 by 2 matrix and it did have 2 linearly independent eigenvectors, right? And so A is non-defective. Long video. Thank you so much for sticking all the way through, and I will see you guys next time for some more general results about eigenvectors.